How's it going, guys? I tried to make a simplified version of this gravibuoyancy theory that I've got. If I ever find funding or somebody else kind of clicks in their head, these experiments are extremely easy to do. They would just cost some money, but it would be very simple to set up. But gravibuoyancy, once you combine gravity and buoyancy together in your head, it all just makes so much sense. So I'm trying to make it more simple. If you want to see the equations and the other stuff, you can check out my other videos. But a concept that is really important to understand, I like to ask people, is when does buoyancy stop and gravity begin? Because once you keep breaking it down smaller and smaller and smaller, all of a sudden they both get lost. So to me, they're actually one and the same. So here's the example. Here's Earth. It's round and spherical, and if you get a sphere of water in space out of containment, it becomes spherical due to surface tension. We can both agree that the Earth and the sphere are spherical because of surface tension. At the end of the day, under the Earth, I know there's other stuff, silica and other stuff in the Earth, everything basically behaves like a liquid, and so it's surface tension on all the layers, and then each layer is a different molecular density, and so you're either moving away from the center or you're drawing yourself toward the center, unless you come up against a surface tension. Like you and me, we want to be at equilibrium, but we're in the air that is less dense, molecularly dense than ourselves, and so we're pressed down below it, but we're stopped by the surface tension of what's right below us on the surface of the Earth. But in reality, we want to be in equilibrium. So in this example, if you look at that sphere of water, if you put a drop of liquid gallium, which is denser than the water, just under the surface tension, if you wait and watched it, it would sink to be the center of the sphere. Obviously if there wasn't a current or other stuff going on like that in the sphere, but it would sink to the center. And in traditional perspective, well, it's just going to the center because of gravity. Sure, there's more mass in the center, but the way I see it is the molecules and the atoms of the gallium, they only interact with the energy that's directly right around them, just like anything else. You only interact with the energy right around you. And so there is a greater input of energy on the closer side to the center than the further side, which creates a draw toward the center. So it's buoyancy and gravity combined. So you can't have one without the other. And at some point, somebody smarter than myself will combine these two theories. They are one and the same. And once it clicks, it makes so much sense, and gravity is so unbelievably simple to think about once you combine these theories. Let me move right along. Alright, gravity and buoyancy are one and the same. See my other video for the equations and stuff like that. All this stuff can be proven so easily. Just like I said, if you add liquid gallium under the surface of the water, it'll be drawn to the center. If you put a bubble under the water, not at just off center, it'll rise away from the center. Same thing if you put a vacuum in there. If you could get a little vacuum bubble real quick, I mean, it would just collapse down, but same concept. The displacement would be balanced out. But let's go back to the air bubble. So if you put an air bubble underneath the surface, but not directly at the center, you'll see it rise away from the center, and then it'll rest up against the surface tension underneath it, and then once that surface tension's broken, the air will be released back out. So moving right along, that experiment needs to be done, because all that's doing is recreating what the Earth is. Heavier stuff goes to the center, lighter stuff goes away, and we just assume because the atmosphere, it just all disappears once you pass the atmosphere. No, there is energy everywhere. We're seeing energy from stars from 1 billion miles away, so we're still interacting with that energy. And wherever there's a direct interaction of energy with the atoms in my body to that energy, it's going to be drawn to that energy. That's what gravibuoyancy is. You know, a galaxy 20 trillion billion light years away that's still getting energy to interact with my atoms is drawing in a traditional sense, the gravitational pull toward it. And that's all it is that there's energy interacting with my atoms. So you got to really break down the large into the small so that they're one and the same. Alright, so I think this is basically what I went over. So if you have an object in space, why is it pulled toward another object? Gravity, question mark. It's the exact same concept, gravibuoyancy. The objects in space give off energy, and the energy an object interacts with in its immediate area is what it is attracted to. Or repelled. You know, you can go either way. What I mean by this is you see a star a billion light years away, the energy you are only directly interacting with, that your atoms are directly interacting with, is what you're attracted to. Gravity in the traditional sense. But your closer side is more attracted than your further, creating a buoyant effect drawing you closer to the energy, or a negative buoyant effect that draws you away from the energy, such as a helium balloon going up in the air. Oh, well, right here I got in here. So negative gravity, can that exist? Absolutely. So positive gravibuoyancy is a helium balloon released at sea level because it is less molecularly dense than its surrounding, and so the heavier, molecularly more massed air will, in one way, it'll create pressure and push it up, and that way that the air is more at equilibrium with what it has that helium balloon's displaced. So I've only been studying this stuff for 3.5 months, so I'm trying to translate it into astrophysicist language, but there's so much red tape in that community, and everybody's got their heads so far up each other's asses. I don't really care. I'm going to keep trying to explain this until it comes out easily, and then if it eventually takes off, great, but I don't really care. This is kind of my Rubik's Cube, Enigma, whatever you want to call it. And like I said, you just gotta harp on gravity and buoyancy. Convert those two things in your head. Break it down to that sphere of water into space and just stick a little piece of rock in it, and what happens? Study that and you'll understand the universe. So to me, everything is extremely simple now that I understand it. Combine gravity and buoyancy. It is absolutely crucial that these two theories get combined. Gravibuoyancy is the word I came up with. It's kind of clingy. I like it. And at the end of the day, no matter what, atoms are just interacting with other atoms, or they're interacting with energy given off by other atoms. That's all that's going on. That's it. And if there's energy, we're attracted to that energy. And if that energy is coming from a billion light years away, we're still attracted to that energy because we're not near that planet. That planet's or galaxy or whatever, its energy is right here. It is right here, right now. It is interacting with my atoms, and it is affecting it by creating a draw, and we draw on each other, and that's the gravibuoyancy force. So quickly, because I started thinking about planetary placement. This is simple also. It's just in different dimensions, which I think kind of gets people. But clearly from this picture from 1990, there are standing waves that are guiding our orbit around the sun. And I did see a video where I saw these waves coming off the sun. And all this is just energy from the plasma and everything going away from the sun. So in these next couple slides, you'll kind of see it. It's very similar to acoustic levitation, but I'll give you examples on the Earth of the exact same concept. So these planetary swim lanes are just standing waves, and I would like to call them acoustical standing waves, but I think it's more of movement of energy waves, if you want to call it that. But let's go see these other examples. So here's a carbon atom with the exact same energy released from the atom, and you can see these standing waves going away from it. And the ratio from the diameter of the atom to the wave is 1.49, and if you look at the planetary placements at their closest orbits, it's 1 to 1.56, so extremely close. It's almost coincidentally too close, which makes me think that it is proportionally the same depending on the mass of the central object giving off energy. So hopefully that makes sense to you. So here's another picture. This is acoustical levitation, which creates the swim lanes around the central point, creating the energy. So same concept in motion, different type of energy, but it's all one and the same. Everything, like Tesla said, everything's just vibrations, energy, and energy transference or something like that. And so here it is underwater. This is kind of two-dimensional, but when water goes over the ground, it creates these ripples. And I get it. You're going to say, well, that's just ripples over space-time. Well, the universe isn't just one giant piece of paper. It's energy interacting with each other and moving, and that just happens to be the frequency that it's in that's going around the rotation of the sun. And that's why looks like a plane when you go around, and it's strange enough, all these planes are in direct relation to the rotation of the mass. So that's just mathematics and physics that can explain that. But I'm sure I get a lot of flack, but I really do not believe that space and time distorts. If you look at acoustical levitation, it looks like a distortion of space and time. So I think maybe that's the interpretation of it. But if you ask me, it's not a distortion of time. I think the perception of time is distorted, but I think the actual electrons are just slowing down, and that's it. But we perceive it as time slowing down. So I guess it could be one and the same, but moving right along. So another example, same thing. Ask yourself again, sorry, I accidentally cut off the slide. Ask yourself again, when does buoyancy stop and gravity start? Zoom into the atom, zoom out to the molecule, which most molecules will try to take a spherical shape, just like the planets in the water theory. Zoom out from the molecule, look at the blob of water, it becomes spherical. Put something with more molecular mass inside that sphere. What atomically is happening, pay attention to that, and you'll see that more molecularly massed item will move toward the center of the sphere. And as soon as you understand that concept, you understand that gravity and buoyancy are the exact same thing. And just because you're in outer space does not mean you're no longer interacting with energy. Now, it may be like massless energy, or very few particles here and there, but it's just less buoyant energy. And so there's buoyant, I call it vectors. I did a three-dimensional breakdown of the gravitational equation, so you can see it in the x, y, and z axis. And so you can calculate these force vectors in space and any type of material you're in to calculate the gravity and the buoyancy. At some point, the two equations will need to be combined better than what I've done, but with the resources and the intelligence I have right now, that's all I can do. I'll throw in the equation real quick. I'll copy and paste it from the other video. You guys have a great day. Bye. So here's the equation visualized. So normally when you have the gravitational equation, it's between like mass of m1 and mass of m2, and in reality you should be able to see all the directions. So to get a true understanding, you can take this all the way down to the atom, all the way up to the galaxies interacting with other galaxies, but this is a way to visualize the equation in 3 dimensions, which gives you a true resultant gravibuoyant vector. So, you can use this for anything. If you're a beach ball on the surface of the water, if you're a helium balloon in the air, you and me, it took me a while to think about, but you and me are just a rock in the pond. Like, we're more molecularly dense than the air around us, so we sink, and we're up against the surface tension of the earth. And what we see on the scales, because we have a resistance force that we can stand on. All right, moving right along. And guys, just bear with me. I've only been studying this stuff for like 2 months, maybe, on and off. Again, one of my friends asked me if I could try and solve gravity. So, in a couple of weeks, I'll think about all this stuff again and see how I can improve upon it. I know it's not a popular opinion, but it's my opinion, so I just wanted to share it with the world. All right, moving on. So, it'll help when you see the next slide where it's visualized, but since I believe buoyant forces and gravitational forces are one and the same, I call it gravibuoyant. The resultant vector, you need to go in 3 dimensions. So buoyancy is only known as up and down. Gravity is really known as up and down, or attraction between 2 masses, but that's not the full picture. The full picture is in 3 dimensions, the x, y, and the z axis. So the way to calculate this is to look at the gravitational equation between M1, M2, and M3, and then you do it to M4, M2, M5, and then also M6, M2, M7. And then once you calculate that, you subtract the energy density of the medium times the volume of the object times the little g, and that'll give you an equation where you're not only calculating the gravitational force, but it also puts in perspective the medium you're in. Because it's not always like it is in the books where you just have a massive object and then nothing in between the 2 objects, and then you have another massive object. Even in space, there's plasma, there's density, there's different energies, and on top of it, it's 2 different worlds when they should be the same. Because if let's say I'm in the magma portion under the mantle, I'm going to have a gravitational pull toward the center, in quotations gravitational pull. I still think it's intermolecular forces. And then you also have buoyant forces up. And so to get your net force, you need to calculate both of these things, buoyant forces and gravitational forces. So I don't like the fact that it's 2 different things. And honestly, the more we get into it, I really think that, if you're in the middle of space, but you just see light from stars, that's still energy you're interacting with. And you being a body of mass, one portion of you closer to that energy is going to be in a different energy gradient than the opposing part. So you have a gravitational pull pulling you toward the energy you're interacting with, which is in the direction of the star, because that's where it's coming from. Because everybody just, they don't quite understand gravity. It's just buoyancy wherever you go. Wherever there's energy, your mass, your energy will always try to find equilibrium because of gradient forces. So take this in. I think there's a better way to write this equation, but I think overall it's on the right track.